So for question 4, part A, what's the maximum number of items that we can insert and not increase the height? So the first thing we can do is, well, actually, first of all, I just want to review what 2, 3 trees are. So for 2, 3 trees, if you have one key, right, then you have to have 2 children. If you have 2 keys, you have to have 3 children. And so these numbers of children correspond to the name 2, 3 trees. And so one invariant of any 2n trees is that the number of children has to equal the number of keys plus 1. And so because here the number of children ranges from 2 to 3, the minimum number of keys you can have is 1, as long as it's not a leaf node. And the maximum number of keys you can have is 2. So keeping that in mind, in part A, we're trying to figure out how many keys we can insert into our red-black tree before we, until we basically fill up our tree without increasing the height of our tree. So for example, any node that has currently less than the maximum number of keys, in other words, just one key, can have an additional key inserted into them, right? So we can insert 4 for a total of 4 single key nodes currently. And then once we insert another node, or sorry, another key, let's say it's 10, then in that case, this node is going to exceed the maximum number of keys a node can have. And so what happens is we need to now push up a key from this node and then continue pushing up through the rest of our tree until we satisfy all of the invariants of a 2-3 tree again. And so what happens is we can just insert or push up the middle key, which is 9, up into this node. And so we get 4, 7, 9 here. And whatever is red means that it's not satisfied by the invariant. And so we need to, change it by pushing up one of its keys. And so what happens when we do this is we split up this 8, 9, 10, or now it's 8, 10 only, into separate nodes. And the reason for doing that is because now this has 3 keys, and so it must have 3 plus 1, or 4 children. But notice that this still exceeds the maximum number of keys. And so what happens is we need to push up the middle key again, which is 7, into its root, into its parent, which is the root. And so now we get this 7, 13, and then this has to have 3 children. So satisfying all that, we get this new tree. Now in this new tree, we also notice that there's still some single key leaves, right? So we still can add some more values to these single key nodes. And notice that I have a 7.5 here. Decimal numbers are actually not part of B trees normally, but for the sake of demonstration, for the sake of an example, I am using decimal numbers. But anyway, what happens after this is if you insert just one more value, right, then you get the same dissatisfaction again, right? You get the same pushing up. And notice that you cannot add any more nodes in this part of the tree, because if you do, then something is going to get pushed up to here. Now this is going to have three keys total, and it's going to push up something to the root. Now the root is going to have 3 keys total. So now it's going to push up something, and that's going to be the new root, right? Which means we're going to be increasing the height. So we cannot add anything more here. And basically what we're trying to do is we're trying to get to the point where we cannot add any more elements in this subtree and also in this subtree, right? Right now we can add more stuff into both of them. So let's actually do that, right? Let's actually add 2 here. And so then we need to push it up. So we get this 1, 4, we push up 1, and everything's fine, right? Nothing is broken. And then we have single key nodes again. So now let's just add some elements to each of them, okay? And then notice that this is also now filled, right? So for the same exact reason that we couldn't add anything more here, we cannot add anything more here. So the only place that we can insert new elements is this subtree. So we do, right? We add 13, okay? And these numbers and also the order in which I insert them is kind of arbitrary. So if I insert 13, this is going to break the invariant, and so now 12 is going to get pushed up, and you will see this, right? Everything's fine though, because nothing is exceeding 2 as the number of keys. But after I've inserted one more element to each of these one key nodes, and I insert one more, and I try to insert one more element, I realize that I can't, right? Because now this is entirely filled too. In other words, every node in my tree has the maximum number of keys, which is 2. So another way that you could solve this problem without going through a painstakingly long example is just kind of mentally picturing in your head, okay, how many times do I need to add to the leaf nodes in order to make all of the nodes in my resulting 2-3 tree have the maximum number of keys. And this is applicable to not just 2-3 trees, but also 2-4 trees, 2-5 trees, etc. All right, and then now for part B, okay, so we start off with the same 2-3 tree given in the question. And now we're interested in kind of the opposite scenario. So what is the minimum number of items that we can insert and increase the height, right? So the first thing that pops to me is that I want to insert something here, because this here or here, basically somewhere in this branch, because I see that I already have this filled to its capacity, and I already have this filled to its capacity. So I know that if I insert something here, it's going to get pushed up to a 3 key node, which is going to get pushed up to the root, and now the root is at maximum capacity, right? So the next time that something gets pushed up to the root, I'm now going to increase my height. So here's attempt 1. Okay, so now I'm considering where I need to insert my next element. Well, just like the same logic here, right? This looks pretty promising to me because, well, because I already have a capacity, a node filled with capacity with its number of keys. So let me just try adding 3 here, and then that will get pushed up to be 1, 4, and then, well, that doesn't really change anything about the root, right? In fact, I need to insert 2 more items to actually increase the height. Why? Because I need to insert 1 here, okay, 1 more here, and then I need to insert, the third one here, which will break this invariant, push one of these up to here. Now this will have 3 keys, and it will push one of them up to the root, which will then increase the height of the tree. So I need to actually insert 2 more times to increase the height for a total of 4 insertions. Let's look at attempt 2. So from this same step, what if we insert it at a different place? What if we insert it into this subtree? Because this is already at its capacity. Even though these leaf nodes are not as full as this leaf node, what actually matters more is that the upper level node is at a bigger capacity, or I guess smaller capacity in terms of how many more we can insert. So in this case, let's say that we insert 27, okay? Nothing happens, everything's fine. But then the third element that we insert, 29, is going to have an effect that's going to increase the height at the end, right? So we're now going to be pushing up, pushing up, pushing up until we get a new tree that has a completely different height. So the original height plus 1. And we can achieve that with only 3 total insertions. So the answer for B is, that's why the answer for B is 3. And the answer for A, as we said, is 13. Okay, so all of these purple highlighted elements are the new insertions that we're doing. So if you just count the number of purple elements, you will get 13. And then similarly for B, although I also keep track of them to the left.